Okay, so this section of the revision video is on stars, what they are and how far away they are from us. So it should hopefully cover everything you need to know about them. Stars are just, like it says here, huge spheres of very hot glowing gas which produce their own light and their own energy by a process called nuclear fusion. Now, stars, there's lots of different types of stars in the universe. There's red giants, there's white dwarfs, there's black holes, they're even a type of star, brown dwarfs, supernova, planetary, nebula. There's loads of different types. However, what our sun is called a main sequence star, and our sun is a bog standard normal star. It's actually on the smaller side of average, so it's not the biggest star in the sky. That it just looks that way because it's closer. It's just a normal star called a main sequence star, and 90% of the stars in the sky are very similar to our sun, although probably a little bit bigger. Now, every single star uses this process called nuclear fusion, but we're going to talk about the nuclear fusion that happens in a main sequence star. So this one here is main sequence fusion. Okay, so main sequence nuclear fusion. Now I'm going to go on why it's different for other ones in a minute. But before we do that, we need to know about the structure of atoms. And I'm going to use the example of helium to help me describe that. So helium is this atom here. Now if you remember, an atom's got three particles in: positive protons, negative electrons and neutral neutrons. Now an atom has two main parts. It has a nucleus and then it's orbited by electrons. Now the nucleus has inside it some positive protons. Now helium has two of these, but the number of protons actually shows you what element it is. So any atom that's got two protons must be helium. Any atom that's got 6 protons is carbon. If you look along the period table, there'll be patterns in there that you'll know, and I'm sure you cover a lot of that in chemistry. So there's 2 positive protons in the nucleus. Then there are 2 neutral neutrons, and I'm going to draw those there like that. Now neutrons, the number of those depends if you're an isotope or not. They don't really affect what element you are. And not every single atom has neutrons, because one doesn't. I'm going to look at that in a second. Now the number of protons you have shows you how many electrons you're going to have, because electrons are negative and overall atoms are neutral. So overall, the electrons, there's 2 of them in this case, orbit around that positive nucleus. So the nucleus is a tiny dense space that's really positive, and then orbiting around that are 2 very, very, very tiny electrons. So this is a helium atom. If I then go on to show you over here a hydrogen atom, which is the smallest and simplest atom in the universe, you'll see in a second, you'll see that there's some similarities. So we still have a nucleus. The nucleus in a hydrogen atom is simply a proton. All it is just a proton on its own. Okay? There's no neutrons there, just a proton. There's 1 proton, so there must be 1 electron orbiting, because we always have the same number to make sure that overall our atom is neutral. So we've got a positive proton in the nucleus and a negative electron. Now if I have 2 of these hydrogen atoms, you can see that if I added them together, I get something like a helium atom, except I'm missing 2 neutrons. So if I can put 2 hydrogen atoms together and add 2 neutrons in, I can basically make a helium atom. And that's what nuclear fusion is. If you look further down here, it says fusion happens when lighter elements are forced together to become heavier elements. Now they're forced together because they have to overcome electrostatic repulsion. So overcome forces to do it. Repulsion forces. Repulsion. Now that happens because it's actually the nuclei that are fusing, not the whole atom, the nuclei of the elements. So the positive proton and the proton nuclei here, they've got to join together. And they're not going to like that, because protons, like magnets, 2 north poles, don't like to join together, don't like to touch. Positive protons are the same. Positives don't like each other. So plus and a plus will repel, a plus and a minus will attract, which is why an electron likes to orbit a proton, but the 2 protons like to be together. So they have to overcome these forces to be joined together. Now when this happens, when I can force these 2 together and add 2 neutrons in, I make something really important, and that is energy. And this is why fusion really happens. And this energy that's produced is to do with E equals mc squared, Einstein's famous equation, but you don't need to know too much more about that. So fusion happens when smaller elements, like hydrogen, are forced together, the nuclei of them are forced and fused together to make heavier elements like helium. Now helium is actually the second lightest element in the universe. In a main sequence star, hydrogen is turned into helium. Now, every single element that's bigger than helium is also made in a star, but it's made in different types. For example, carbon is made in red giants, and the really heavy elements like gold and uranium are made in supernova, which are huge explosions that we're going to talk about in just a second. But every single element in the universe is made in a star. So everything that you have around you, everything that is you, is actually made of stardust. So when they say that, they're actually telling the truth. It's just that they're made in bigger, more powerfully burning or hotter stars. So, now we know what a star is and how it burns, how do we know how far away they are? Okay, now we obviously look at stars through telescopes, or we can see a lot of them with our own eyes, but not that many compared to how many there are in the sky. But how can we work out how far away they are? Because if you look at a star, if I draw two stars up here, I have a smallish star there and a really big bright star here. Now, what's to say that this small star here isn't bigger than that star just further away? So how big a star looks depends on two things. It depends on how bright it is and also how distant it is. So we can't just say, oh, the bright star is the closer one, most of the time. There's one exception that I'll talk about in a minute. Now for nearby stars, we can use something called the parallax method. Now you don't need to know much about this, you just need to know what the kind of idea is, and you need to be able to label a diagram like this. Now if you hold your finger out in front of your face, just one of them, hold it up in front of you as if you're showing someone the number 1, then you close one eye and then close the other eye. So you're winking continuously at your finger. You'll see that your finger appears to move from side to side. Now if you slowly bring it towards your face, you'll see that that finger seems to move more and more and more. Now that is a parallax effect. Parallax is just a shift in apparent position. Now the Earth is kind of like your two eyes. Remember, the Earth orbits the Sun every year. So this is the Earth and that's the Earth orbiting the Sun. This is the Sun here. Okay, and this is the Earth. Now, it takes a whole year to get around. So if this is the Earth in January, then this position here must be the Earth in July. Now, when the Earth is in January, if you think of this side on, you think of this as two eyes and the Sun as your nose, when you open this eye and you look at your finger looks like it's here against the background of the room. When you open the other eye and you look at your finger looks like it's here. It's exactly the same with the Earth and the stars. Okay? So if you look at a nearby star, in January, it's going to look as if it's here against these distant background stars. Now these background stars are so far away, you know, they don't look at here. These are distant stars. They're far away, so they don't really move. I don't have to write distant, far away. I think you know what the two words mean. They don't move, okay? So they're fixed because they're so far that parallax doesn't really work for them. This here is my nearby star, and it appears to move throughout the year. So here I've got my apparent position in January, because you can see from the line of sight across there, that's how it looks in January. And this is the position in July. Because from the line of sight you see it there. Now you can see this has made a triangle. Now I know this distance, I know how far it is to the Sun. And I can work out what this angle is. Okay, I know that as well. Now this is a right angle here, so I can just use trigonometry to work out this distance. Okay, and that is using trigonometry. And this is what scientists do, this is what physicists do. They look at these nearby stars and just work out what this distance must be by working out this angle and this distance. Now these angles are tiny and this distance is tiny, and it's not the world's most amazing method, but it's really useful. So what you really need to know is this diagram and this. The Earth's orbiting of the Sun causes near stars to seem to shift their position, that's the most important thing, against distant stars over the course of the year. And this is called a parallax shift. Scientists can use this idea to work out about how far away this star is. And that's really useful because we know how far away our closest stars are. Now there's another method which we can use for some certain types of stars. That's called the brightness method. Now we talked about we can't just say, oh, it's a brighter star, therefore it must be closer, because a really big bright star that's far away might look a bit dimmer than a really close dim star. However, there's luckily something called supernova. Now, supernova are huge explosions of dying stars, and the word in Latin means big for super, and nova means new, and actually it means big, bright, new star. Because when these stars come into being, they're not there for that long, because they're huge explosions, but they're massive, and some of them in the 1500s was on so big that the night wasn't dark for a few nights, because the explosion was brighter than the sun, even though it was billions of miles away. They're quite rare, they only happen about once a century in every galaxy, but if you look close enough for long enough at a galaxy, you will see one. Now, a certain type, so I think called type 1A supernova, are all the same brightness, and that is really useful, not useless, because if I have two type 1A supernova in two different galaxies, and there's this one like this, there's this one like this, so this really bright one is in galaxy 1, and this really bright one, is not very bright one even, is in galaxy 2. Now, if I know that they're the same brightness, then surely this one in galaxy 2 must be further away. Because if they're the same brightness and one thing looks further away, if you've got two light bulbs that are the same brightness and one looks dimmer, then you know it's further away. That's another method we can use, but it's limiting because it doesn't always happen. There's not many of them, and you have to have your eye on that galaxy with a telescope, not with a human eye. Now, all of these methods have got a few issues. Now, we use telescopes to look for our stars in the sky mainly. We don't really rely on human eyes because they can't see enough and they can't keep their eyes fixed for long enough. Now, there's two main difficulties with telescopes right nowadays. One is light pollution. If you've ever been to the countryside, or especially like a desert, and you look up in the middle of the night, you will see thousands and thousands of stars in the sky. If you look up in the middle of London or any other city, you'll only see a couple, and that's because only the brightest stars can get through the brightness of the sky at night in cities, because of all the artificial lighting that we have. So telescopes need to be far away from that. The second thing is also the atmosphere. Now, the atmosphere plays a huge problem because it's lots of air that's moving around. Now, obviously you get clouds and stuff, which is obviously an issue if you're going to be looking up at the skies, because if you've got a cloud there you can't see. But also something called turbulence, which is just the air moving in the atmosphere, makes the stars like they're twinkling, and that's where you get twinkle twinkle little star from. They twinkle not because they're actually twinkling, but because the light from them is being distorted by the atmosphere. Now, we get around this by making our telescopes, or putting our telescopes, I can't spell what I'm thinking, telescopes, on mountains, okay? Because mountains are really high up, so there's less atmosphere, and there's no light pollution because people don't really live on top of a lot of these mountains. They're in places like Hawaii, I think there's one in Lanzarote, there's some in Chile. Coincidentally, they're also good wine growing regions because that's the kind of conditions that you need. And that can get around that kind of problem. The next problem we have is kind of harder to get around, and that's the uncertainty in our measurements. So uncertainty in measurements. And that's because these methods are really tricky. And if you make one mistake somewhere, then that can have a knock-on effect and multiply as you do more and more sums with that measurement. So using this brightness method, if you make a mistake in the first measurement, it may mean that the rest of your estimates that you make aren't as good. So it's really, really hard to measure the distance to stars. It's one of the hardest things to do in astronomy. But the main reason why is because of these uncertainties in measurements. We have difficulty seeing stars because of the conditions on Earth. But then because we can't just get a ruler out and measure the distance, we find it really difficult to measure them as well because of the uncertainty in our calculations. So, the last thing we need to think about is this. Are we actually looking back in time? And we're going to talk about why I've said that in a moment. But the speed of light is finite, okay? Now finite, just check that's still straight. Finite means that it's fixed, okay? It's not infinite, basically. So the speed of light is this, 300 1,000 kilometres per second. Okay, it's really, really fast. It is the fastest thing in the universe. Okay, you can't go faster than light. Whatever you say, it can't go faster than light. It's the fastest thing in the universe, but it's still not infinite. So when you turn a light on, it actually takes a picosecond or so for the light to get to your eye. The sun, it takes like 8 minutes to travel from the sun. So if the sun exploded, we wouldn't know for 8 minutes because we wouldn't be able to see the light. Now, a lot of people use the idea of light years. Now, light years are nothing to do with speed, they're actually a distance. A light year is the distance light can travel in 1 year. And it's equal to the speed of light times how much time there is in 1 year, which is equal to 300,000 times 60 for the number of seconds in a minute, times 60 for the number of minutes in an hour, times 24 for the number of hours in a day, times 365.25 for the number of days in a year, including leap years, and it gives you something like this, 9.46 times 10 to the 12 kilometres, which in non-standard form, which is this is called, is 946 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros after it. And as you can see, that's a really, really big number. So that's how far light can travel in a year. Now, that's still quite small in astronomical terms, because the closest star, Proxima Centauri, is 4.2 light years away. The closest galaxy is 2.5 million light years away. So when we look at Andromeda, or when I look at the closest star, Proxima Centauri, I'm seeing it in the past. When I look at Andromeda, so this is where the looking back in time part comes into play. When I'm looking at Andromeda, Andromeda is 2.5 million light years away. I'm looking at it 2.5 million light years ago, or 2.5 million years ago. So Andromeda might not be there anymore. It is. But if it had exploded in a random explosion and all been destroyed, we wouldn't know for another 2.5 million years. We're looking at it 2.5 million years ago. So basically we are looking back in time. This is a really, really useful thing to be able to do because we can look at how the universe was in the past by just looking at really distant stars. And it's a really useful thing for the Big Bang Theory, which is what we're going to go on to in the next video. So I hope that was useful. I hope that's everything you need to know about stars and how to calculate how far away they are. Thank you.